Assalamu alaikum warahmatullahi wabarakatuh. This is Dr. Ali El-Moursy and I am recording lecture number 23 part 2 for Digital Logic Design DLD, and actually in this lecture we want to continue how can we build the different storage, the different memory cells, as well as going over the slides for going over the introduction. Actually this slide number 2, which is actually showing us the system for sequential circuits that has actually two types of inputs, as we discussed before. We have the external inputs as it is shown here, we have the outputs and the memory device inherited inside the system, and we have the output from the system. Part of it or all of it is actually connected through the feedback back to the system as a secondary or the second input. So the sequential circuits usually have two types of inputs, the external inputs and the internal inputs, as we will go over them later on the analysis and design for those types of circuits. As you can see that the system should have a memory in order to store the data and to be able to feedback these data back to the system in order for the further processing. Sequential circuits, by the way, have two types, something called asynchronous, which we will start with, and the other type of the sequential circuits called the asynchronous circuits, and we will describe and discuss the difference between the synchronous and the asynchronous, inshallah, in the next parts of the this chapter, in the lecture number 24, inshallah. So the first thing that we want to discuss in this chapter, as we mentioned, is the memory cell that is able to read and write. The memory cell that we have developed in the part number 1 was actually only a RAM cell, through which we actually connecting two inverters back to back. Now if we want to build a real memory cell, the first memory cell that we will be able to build is called the SR latch. The SR latch, the latch here indicates that the logic is stick into the circuit until some excitation of the inputs to change the stored value, if this ever happen, as we will see and demonstrate fully in the next couple of slides. As you can see here, this circuit diagram that is shown up there in the up right part of your slide is actually showing a very similar circuit to what we already have developed in part 1 of lecture 23. However, here we have replaced the inverters. We have replaced the inverters that we have shown in the board before. We replaced them with NOR gates. The advantage of using NOR gates is now I have actually two inputs per gate. I have two inputs per gate. One of those inputs is coming from the feedback, as we explained before, which is considered to be the internal input of the circuit. However, replacing the inverters with NOR gates will allow us for one extra input per gate. So I have here the red NOR gate number 1 up there and another green NOR gate, which is number 2. Now each of them has a one extra input, which is an external input to the circuit. The first one connected to the red number 1 NOR is we call it R, and we will explain why we call it R, and the other one is we call it S, and we will also explain why we call it S. So we have two external inputs, R and S, and we have the output as it's shown here, the Q, and as we indicated, the output from the other gate is called Q bar. In sequential circuits, what you see on the circuit as an output, which is Q and the Q bar, during the analysis, as we will see here in the rest of the slides and the analysis, the output that you see as an output, which is usually connected to the feedback as an input or internal input, it is actually during your analysis is an input, not as an output. The circuits, the digital logic circuits, the sequential circuits, okay, has two types of inputs, external inputs and internal inputs. And as their name input, they are input to the circuit, and they effectively also shown on the circuit as an output. However, during your analysis, the output is not what you see on the circuit as an output. When we mean by the output for synchronous sequential circuit is the output in the future. As we indicate, this circuit is changing, which we call it the state. It's changing its state, which means changing its Q value over the time, because the circuit is time dependent. So in order for me to successfully and accurately analyze the circuit, I am actually dealing with that output, which we call it the state output, also called the state input. Okay, the state input here is actually used as an input during our analysis. Accordingly, the output that you want to actually drive is the exact same parameter but in the future. So Q is an input, okay, also Q bar here is an input. Type, where is the output of the circuit? The output of the circuit, we have to give it another name, so we call it Q of t plus tau, to indicate that this is the output of the circuit in the future. So we have two different distinct components here. Q is the input of the circuit, and the Q in the future is the output of the circuit. Also we call it the state input output, which is usually connected to the feedback. These are rules and regulations that we have to follow while we are analyzing the sequential circuits. The second condition that we have to deal with here is that the output is actually should have two faces. We have the output and the output bar. The output and the output bar. If the circuit do not produce the output and its complement, that means that the circuit is not working properly. The circuit has some malfunction, as we will see during our analysis. Now, the gates that we can see here are just simply a NOR gates, and we already know the TT for the NOR. So if I have a NOR gate, that means I know that the inputs for the NOR, two input NOR gate, if it has X and Y inputs, so it can describe through the simple TT that we can see here. 0 0 showing will give me 1, 0 1 show me 0, 1 0 give me 0, and 1 1 give me 0 after time tau, as we agreed in the analysis from chapter number 2. So now we are ready to do a full analysis for our circuit. Right now we need to analyze this circuit for getting completely the feedback. Now you can break the feedback and you can deal with the inputs and the outputs in the future after tau for the circuit. The inputs for my circuit here are only 3 unique inputs. They are the parameter R, the parameter S that are shown here. Those are the external inputs. We have also Q, which we agreed to deal with it as a third input. What about Q bar? Q bar by definition is the complement of Q, so it is not one unique input. That's why our table here shows S, R, Q, and automatically Q bar is the complement of Q. So accordingly, effectively, from the digital logic point of view, we have a circuit that has 3 unique inputs: S, R, and Q. And the Q bar is the complement of Q by definition. Accordingly, since we are analyzing a digital logic circuit with 3 inputs, we want, in order to analyze it, we need to drive the truth table for its outputs. The outputs, as we agree, are the Q and the Q bar in the future. And the first thing that we can do on TT here is to list all possible combinations of the inputs. Since we have 3 inputs, that means we have how many rows? We have total 8 rows. So we have for the inputs S, R, and Q 0, 0, 0, 1, 0, 0, 0, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 0, 1, 1, and 1, 1, 1. Those are the all possible combinations of the 3 inputs for the circuit. As we agree, Q bar is the complement of Q. Now, to analyze the circuit, we want to drive the TT for the outputs. We have 2 outputs. We have Q at T plus tau and the Q bar at T plus tau. The inputs on those NOR gates will take tau propagation delay to deliver or produce new values for Q and for Q bar. How can we drive those Q and Q bar? Simply by following the rule of the NOR. So if we are analyzing the first red NOR gate, number 1, it has inputs R and Q bar. So we have the row or column for R, we have column for Q bar. We can simply drive the column for Q at T plus tau. 0 NOR 1 from the NOR gate is 0. 0 NOR 0 is 1. 1 NOR 1 is 0. 1 NOR 1 is 0. 1 NOR 0 is 0, and so on. 0 NOR 1 is 0. 0 NOR 0 is 1, and so on. So we can easily drive this column for Q, which is the output at T plus tau, from knowing the R and the Q bar for the first NOR gate. Convinced enough? Is this correct? Now we shift to the next NOR gate. The next NOR gate, we will repeat the same thing. We have column for S, we have column for Q, so we can drive Q of T plus tau dash, or Q bar of T plus tau. Again, following the NOR rule. So this NOR, 0 NOR 0 is 1. 0 NOR 1 is 0. NOR 1 is 0. 0 NOR 0 is 1. 0 NOR 1 is 0. 1 NOR 0 is 1 NOR 0 is 0, and so on. 1 NOR 1 is 0. 1 NOR 0 is 0. 1 NOR 1 is 0, and so on. So we drive the column for Q bar at T plus tau. So all of this is after T plus tau. Now the original q and q bar at time t is now history, because actually we lost them. They are not exist anymore. Now they are replaced by q of t plus 1 and the q bar of t plus 1 of t plus tau. Q of t plus tau and the q bar of t plus tau. These are the new inputs for my feedback circuit. So we can repeat the analysis. Now we have S and R external inputs, and we have internal feedback at t plus tau, q and q bar. Can we repeat this process again? The answer is yes, similar to what we did before. Through the NOR we can know 0 NOR 1 is 0, 0 NOR 0 is 1, and we can drive a new column for q at 2 tau from the QR and the q bar at tau. So we drive this column for q at t plus 2 tau. Similarly, we can drive the column for q bar at t plus 2 tau. Okay, again using the NOR functionality. Luckily, the circuit do not need to be analyzed for times beyond the 2 tau. We don't need to analyze it beyond the 2 tau because the circuit will be in a stable state. There is no further change that will happen for q or for q bar after 2 tau. If you don't believe me, if you don't trust me, just try to do that and try to drive any t plus 2 tau or 3 tau. You will not find any further changes to neither q or nor q bar. Now we need to analyze what happens to the circuit, how this circuit works, what is the different functionalities for this circuit. This circuit has 4 types or combinations of external inputs, S and R. We need to analyze for each of those cases what is happening to the output of the circuit after tau or after 2 tau. So we can here go and check. Now when S and R both are zeros, okay, there are 2 values of q, either q1 0 or q1. After 2 tau we have noticed that if originally q is 0, it will remain 0. If q is originally 1, it will remain 1. That means the circuit from inside do not change the stored value here. This is the case, by definition, the case for reading, because when you set S and R both to zeros, the circuit will remain producing the same output. If it originally gave me 0, it will remain 0. If it give me 1, it will remain 1. And the same thing or the opposite for the q bar. That means when I put S and R, the values for S and R to 0 0, this is the case for reading. I am reading the content of q. Okay, next is when I put S and R 0 and 1. When I put S and R 0 and 1, again I have 2 values for q, q0 or q1. When I have q0, I ended up of q also 0, no change. But when if originally the circuit is giving me the value of q equals to 1, this 1 after 2 tau will change to be 0. That means no matter originally the circuit here inside is storing the value 0 or storing the value 1, the stored value after 2 tau will change to be 0. And we call this the case that when S0 R1, I am storing the value 0 or forcing the content of the cell to be at 0. That means I am storing or writing to the memory cell the value 0, and Q bar is the opposite. In the third case, when S equals to 1, R equals to 0, again we have the two cases for Q, 0 and 1. If I originally storing the Q equals to 0, this Q will change to 1. If I'm originally storing 1, this will remains 1. That means no matter what is the original value of Q, after 2 tau, the circuit stores the value 1. That means I am setting or writing to the memory cell the value 1. So SR00, I am reading. SR01, I am writing 0. SR10, I am writing 1. So I actually satisfied the 4 conditions for a RAM cell, because all what I am looking for from a RAM cell is to either use it for reading or writing 0 or writing 1. And the 3 functionalities have been satisfied here with the 3 values or combinations of SR00, 01 and 11. The last case here is a very weird case. As you can see here, this case I'm setting S and R to 1s. Again, if I try to analyze the circuit, I have Q 0 or 1. In both of those cases, Q equals to 0, which may deceive you, think that it is the case of writing 0 in the cell. However, if you, with a closed look into the other output of the other NOR gate, you will find also Q bar equals to 0, 0. This is impossible to happen, to have Q and its complement are equal. So that's why we call this the unstable or forbidden state for the circuit. So whenever you are using the SR latch, never put both S and R to 1s, because this sends both the Q and the Q bar to 0s and will put the circuit in what we call the unstable state, as we will see its demonstration shortly in the following slides. Okay, so this is actually the summary of how the SR latch is working, and we can actually summarize that inshallah in the couple of slides later. Okay, now in order to appreciate more that we claim that the case for S and R are a forbidden case, we wanted to further analyze this case. Now, from the previous slide, we have actually shown that the last case for S and R is when we have S and R both are equals to 1s, and we have shown that Q and Q bar after 2 tau are both equals to 0s. Why we call this an unstable or a forbidden case? This we want to further discuss and demonstrate in the next slide. So in this slide, we assume that we will start with the case that we have ended up in the last slide. Now I have Q and Q bar are both 0s, which falsely, deceivingly, maybe indicates to the user that I am in a writing 0 state. But right now Q and Q bar are both 0s. Now I want to change the value of S and R from both 1s to both 0s. And let us go over the analysis of the circuit to see what will happen in our circuit in this case. Okay, now going back to our time analysis, we have this Q and Q bar at time t, and we want to drive the Q and Q bar at t plus tau and t plus 2 tau. At t plus tau, we will just apply the rule for the NOR. R Q bar, the output is Q at T plus tau. 0 NOR 0 from the NOR will give me 1. The same thing for the other NOR. 0 and 0 through the NOR will give me 1. So that means Q and Q bar have changed their values from both zeros to both ones. If I further do the analysis for the circuit, I can also drive the outputs at T plus 2 tau. And now I have R0, Q bar 1 at T plus tau. So Q at T plus 2 tau through the NOR 0, 1 will give me 0. Okay? The same thing for the other NOR. 0, 1 will give me 0. Can you see what happens to the circuit here? The circuit turns to be unstable because automatically and endlessly the Q and the Q bar will go from both zeros to both ones, to both zeros to both ones, and so on. So the circuit will never stabilize, because here I cannot use it either for reading or writing, because the Q and the Q bar turns to be unstable. One time I read it, I will find it 0. One time I read it, I will find it 1, and it will go like that forever. The circuit starts to oscillate. That's why it is highly recommended never to send or make or cause the SR latch go to this unstable state by never applying the 1-1 in the SR latch. That's why we call it a forbidden case. Okay, so accordingly, here we wanted to summarize in a table which we call it the characteristic table, that actually show me how the SR latch is working. So SR00, so I am no change, so the value for the output will remain Q. When I have SR0 and 1, I will have the output will be forced to reset. Why we call it reset? Because actually here R is 1, that's why we call it R. So R for reset, S for set. So when R equals to 1, S equals to 0, Q will be zeros. Okay. For S1 and R0, this call it the value set, or writing 1 into the cell. So the output will be 1. For 1 and 1, this is the forbidden case or invalid case. Never do it for the SR latch. Okay. As the slide shows here, there are other implementation for the NOR using for the SR latch, using instead of NOR using NAND. And this part of your homework, you have to go and try to analyze or repeat the analysis that we have done for the NOR, repeat it for the NAND to show what will be the output of the circuit. So we will stop here at this slide. This is actually lecture 23.2 or the second part. Inshallah, in the next lecture, which is lecture 24, we will discuss more different flavors of the SR latches circuits in order to get rid of the forbidden case and have a more mature circuit, as we will see inshallah in lecture number 24. Thank you, and see you in the next recording. The chapter number 5, starting with a little bit of revision of what we have already learned in chapter number 5, and then we will go to the building of the memory cell, the RAM cell.